Hi all. This lecture is devoted to establishing Marton's conditional transportation cost inequality, which is the following transportation cost inequality that we found last time was very useful in allowing us to prove concentration inequalities for functions which satisfy properties weaker than bounded differences or the McDiarmid setting. So we did that in the last lecture, and all that was remaining was to prove this kind of transportation cost inequality. So what is Marton's conditional transportation cost inequality? Just to recap, it basically says that if you're given two probability measures, one is P, which is a product measure, and one is Q, which is some uh, absolutely continuous measure with respect to P, then there exists a coupling between the P and the Q measures. Let's say for random variable sequences x and y of length n, such that the expected value of the sum of the conditional discrepancies squared is bounded by basically the divergence between these measures, the KL divergence between the Q and the Pn. Okay, so that was the content of Marton's conditional transportation cost inequality. We have already proven a similar related inequality, which is Marton's transportation cost inequality, basically where there was no conditioning on x or on y. And we were able to establish there that the inequality still holds, that you can bound the left hand side by a quantity based on the divergence. And we will follow a very similar proof template for doing the same exercise here. So the proof is going to be as before, induction by induction on the number of variables n. So just as we did earlier. Okay, so for Marton's transportation cost inequality. So so there are two arguments in an induction proof. So one is basically the induction step, and one is how you prove the base case. Let's look at the induction step before we go over to the base case. So what is the induction step here? So the induction step consists of assuming that for all n less than equal to, let's say, some arbitrary integer k, there exists a coupling between xn and x1 through n and y1 through n, okay, which have individuals marginal p1 through n and q, such that the inequality star holds, where star is going to be denoted. So this is star here. So let me make it red. Okay, so let's assume that this statement holds for all n at most some integer k. What we will do is to show that the same inequality holds for n equal to k plus 1 by building a new coupling. Let's build a coupling. Let's now couple using this one length, so the sequences of length 1 extra. So x k plus 1, let's couple x k plus 1 to y k plus 1 with desired marginals p k plus 1 and q, such that, so note that when we say p k plus 1 and q, it's just sufficient to consider q or the marginal distribution of q on the first k plus 1 symbols, such that star holds for n equal to k plus 1, thereby extending the induction hypothesis by 1 unit. So it's the idea is exactly the same as what we did to extend the induction hypothesis for Marton's transportation cost inequality. So what is the idea here? So in words, what you have is that you have let's say you have a coupling in your hand, which can couple x1 through xk to y1 through yk. Okay, so you basically have a coupling between these two. And what we would like to do is to extend this to a coupling between k plus 1 length sequences on the top and the bottom. So what you do is that having the y sequence conditioned on the first k y's, this basically gives you a conditional distribution for the k plus first place. So q of dot given, so let's say q of the k plus first entry being something given the first k entries, and you also have a target marginal distribution for the top side, the xk plus 1, which is just the distribution of xk plus 1, which we also called pk plus 1. So having conditioned on the realization of phi 1 through k, what you do is you take this measure, the conditional distribution of yk plus 1 given the first k y's, and couple it to the x target distribution, which is pk plus 1. So couple conditionally, because we are conditioning on the yk here, y1 through k here, using the n equal to 1 uh, result. So recall that we've assumed the induction hypothesis to hold for all n less than equal to k. So that means it also holds for n equal to 1. And basically that allows us to find a coupling or use a coupling between pk plus 1 and this conditional distribution of yk plus 1 given yk to generate this new pair xk plus 1 yk plus 1, which we just append to the end. Okay, and we will be able to argue that the entire joint thing between x1 to xk plus 1 and y1 through yk plus 1 is the desired coupling on k plus 1 length sequences with designed to have the appropriate marginals, that is p on the top part on the x side and q on the y side. Okay, so formally what we do is we begin by using the n equal to 1 construction conditionally on conditionally on basically the previous k the realization of the y's. So this just means for all realizations y1 through yk. So what is this construction that we are guaranteed to that is guaranteed to exist? There exists a coupling between xk plus 1 and yk plus 1 distributed that couples the distributions pk plus 1 or pxk plus 1 with the conditional distribution of yk plus 1 given the first k y's are equal to small y 1 through k. Okay. So also we know that this n equal to 1 conditional coupling also satisfies the inequality for n equal to 1. So that the inequality basically reads expected value of the probability. So this is the n equal to 1 form. So the variables being measured for discrepancy are just xk plus 1 and yk plus 1 given. So this is all conditional on conditioned on y1 through k. So we should always condition on y1 through k. Firstly, there is the conditioning on one of these variables itself, followed by the background conditioning y1 through k equal to small y1 through k whole square, plus the same thing where the conditioning is on the x variable. So xk plus 1, and we will add to it the background conditioning yk equal to yk the whole square is upper bounded by twice, this is the induction hypothesis for n equal to 1, twice the divergence between q yk plus 1 given yk equal to small y1 through k with pk plus 1. Okay, this is what the induction hypothesis guarantees us. Let's call this statement as statement 1. And now how do we build this coupling? So now we are going to define the formal extension or a new coupling between x1 through k plus 1 and y1 through k plus 1. So let us set p x k plus 1. So the joint distribution between the k plus first x and the k plus first y, condition on xk yk, the previous k-length segment, to be equal to, let's define this to be equal to generating using this guaranteed coupling for the last two variables of the x and the y sequences, xk plus 1 yk plus 1 conditioned on yk alone. Okay, so what this means is basically that it exactly executes this diagram. You take the first k y's, from then that gives you a conditional distribution on the k plus first y, and just use a coupling that can couple this conditional distribution for yk plus 1 with the standard distribution pk plus 1 for the xk plus 1. Okay, so this is how we inductively define. So this basically defines a probability distribution on x1 through k plus 1 and y1 through k plus 1. Okay, so now we have, basically by doing this, we have ensured a Markov chain. We have defined basically a Markov chain that says that if you have xk, from it you can generate yk, just because you have a joint distribution between xk and yk. This is using the existing coupling, the induction hypothesis coupling for n equal to k, and from there yk alone is enough to generate the next pair xk plus 1 yk plus 1. Okay, and thus as a consequence of this, we can write that the probability xk plus 1 not equal to yk plus 1 given xk plus 1 and yk. So recall that this is just this term here. Okay, this term is being analyzed. Conditioning is on xk plus 1 and the background conditioning on yk. This is just equal to, so recall what happens here. If you map it to the Markov chain diagram here, it's the probability of some event involving the rightmost Markov chain element conditioned on a part of it itself, which is xk plus 1 and yk. So we can add by the Markov property xk for free, x1 through k for free. Okay, so what the Markov chain picture means is that for free, because of the Markov property, we can add xk plus 1 yk, and we can add for free x1 through k. And now if we just combine these two elements, it's just the entire vector x1 through k. Given x1 through k plus 1 with y1 through k. So let's record this as statement 2. So we are just analyzing the terms in this n equal to 1 inequality. Okay. Now let's come to trying to prove. So we can manipulate this inequality further if we can find a lower bound for the first term here, the first condition probability here, and so that is done by using Jensen's inequality. So notice that so let's say also by Jensen's inequality. So in fact expected value of the probability of xk plus 1 not equal to yk plus 1 given xk plus 1 the whole square. So let's analyze this term, an expression of this form. So in fact let us write the Jensen inequality conditioned on, in its conditional form, xk plus 1. So this is just the same as the expected value. Probability is just expectation of an indicator, and one can write, so let's start, let's write this step by step. The inner probability which is being squared is just the expected value of an indicator event, condition on xk plus 1, the whole square, okay, whose expectation is being taken outside. Okay, now what we can do is we can write the inner expectation, which is the inner conditional expectation, as a further conditional expectation, where in the first level you take the expected value of xk plus 1 not equal to yk plus 1, conditioned on two things. One is xk plus 1 as usual. To it we add an additional yk. Okay, and imagine taking the conditional expectation of this with respect to xk plus 1. So by the law of iterated expectation, uh, this double expectation is the same as this expectation. Okay, and so all we are doing is we are writing the inner conditional expectation as a further expectation on an extra quantity which is yk, and then we are squaring it. Okay, now let's apply Jensen's inequality to this conditional expectation with respect to xk plus 1, which is being squared. Okay, so when we do that, so it's the square of an expectation, because the square is a convex function. We can basically bring the conditional expectation outside the square. We can bring the conditional expectation outside the square. Yes. So less than equal to the expected value. The outer e remains the same. And so imagine bringing the conditional expectation outside the square. So what you have is the thing that comes out combines with the e outside. Okay, and then what is left inside is the probability that xk plus 1 not equal to yk plus 1, given xk plus 1 comma yk, the innermost probability, which gets squared. Okay, so this is basically Jensen's inequality for the square function. It's in its conditional form that we applied. So let's put 2 and 3. So if you take 2 gave you an equivalent form. Let's put 2 and 3 into 1. So let's go back to equation 1 here. If you look at equation 1 above, what equations 2 and 3 have helped us do is to basically give a lower bound for the second term on the left hand side. So we can now go back, and using 2 and 3 into 1, we can write the following. So let's say putting 2 and 3 into 1, we get this following simple form: expected value of p, the conditional probability of discrepancy at the k plus first position, given the entire x vector plus p xk plus 1 not equal to yk plus 1, the same conditional probability given the entire y vector up to k plus 1, is just at most the divergence between the conditional measure q k plus 1 given y 1 through k with respect to p xk plus 1 or pk plus 1, it's the same thing, conditioned on qyk. Okay, so this notation is just saying that right. So what we have is basically that uh, so what we do to equation 1, to inequality 1, is just that we put in these expressions, and then since the left hand side now, and then we take expectation over yk. Okay, we just take expectation over yk to get this. Okay, now right, so we get this equation 4, and So now what we want, so we can now go ahead to finish the proof of the induction step, the extending the induction hypothesis. At the top level, what we wanted to do to extend the induction hypothesis was to prove a bound on the following expression: sum over I equal to not k but k plus 1 expected value of p xi not equal to yi given x up to k plus 1 square plus p xi not equal to yi given y up to k plus 1 the whole square. Okay, so we wanted to basically bound this using the K divergence, but we can already see the following from, so let's now look at it from the point of view of the coupling we have constructed between x1 through k plus 1 and y1 through k plus 1. We have that for all I, so let's look at I at most k. Okay, so let's look at the first k terms of this sum, any term in the first k terms of the sum. So for any such I that is at most k, we have we have that this expression is just equal to probability xi not equal to yi given xk and xk plus 1. This is by definition x, this is everything up to k and then the k plus first element. But by our coupling construction, basically it doesn't matter whether k plus 1 is there or not, okay, because xk plus 1 is really independently generated of xk comma yk. Okay, xk plus 1 just follows its own distribution pk plus 1. So once xk is there, the conditional distribution of xi comma yi just depends on xk. It does not depend on xk plus 1 just because of the nature of our particular coupling. Okay, so since xk plus 1 is independent of xkyk, okay, that's the reason. The other term here for any the conditioning or yk plus 1, so this is just equal to so for any I at most k, this is just equal to the probability that xi not equal to yi, okay, given, so recall that yk plus 1 consists of yk and the y all the way up to k and then the last yk plus 1. So again we can drop y the last yk plus the k plus first element of y, since we have the Markov chain yk, so yk plus 1 just depends on yk and it does not depend on xk. Okay, so yk plus 1 is irrelevant to find the conditional probability of xi not equal to yi given all the first k plus 1 elements, okay, because of this Markov chain structure here. So what we have finally is that this is equal to, so if you split this sum into two parts, one containing all terms up to k and one containing the k plus first term, so in the first sum up to I equal to 1 through k, we will use these equivalences and we can essentially, this allows us to replace k x all the way up to k plus 1 with x all the way only up to k plus p xi not equal to yi given y all the way up to k only. And then we have the last term, which is the term initialized at k plus 1. So that's p x k plus 1 not equal to y k plus 1 given x all the way up to k plus 1 the whole square plus the same thing, same event conditioned on y k plus 1 whole square. And now we are in a position to finally bound this. We'll use the induction hypothesis on the first sum. Okay, note that we have massaged the first sum into exactly the form that the induction hypothesis for n equal to k guarantees us, and we will use inequality 4 on the k plus 1 part, okay, on the remaining part. So let me say induction hypothesis for n equal to k plus inequality 4. This is what gives us the authority to write this as upper bounded by t q yk with pxk plus by 4, the right hand side of 4 is basically q yk plus 1 given y all the way up to k with p xk plus 1, which is itself the conditional distribution of xk plus 1 with respect to xk given q yk, and by the chain rule of KL divergence, this is exactly what we need, which is 2d q yk plus 1 with p xk plus 1. This is by the KL divergence chain rule. Okay, so that basically completes the induction argument. It only remains to now show the base case of Marton's conditional transportation cost inequality, which is n equal to 1. So we just have to show the inequality holding for the n equal to 1 case. So for this, let us introduce some new notation. Let's introduce this new notion of distance between two probability measures, which we will call D2QP, distance or divergence between probability measures, as the sum over x of px minus qx. So we are doing this for discrete distributions only, but it can easily be extended via the Radon-Nikodym derivative mechanism for arbitrary distributions. Okay, all under the square root. Okay, where the plus notation just means that so x plus, for instance, is just taking max of x with 0. So it just gives you the positive part of x. You can also write it in terms of the 2 norm over of random variables as it's the L2 norm of the Radon-Nikodym derivative of 1 minus dq pi dp, the plus sign here, and the 2 norm as defined in the standard. So it's the 2 norm of any random variable is the square root of the expected value of its square, okay, square root of its second moment. So here's a lemma which is very similar to the sort of a transportation cost lemma for the total variation distance. So we have that given any two random variables, any two distributions p and q, there exists a coupling xy of p and q such that the least value of e p x not equal to y given x the whole square plus p x not equal to y given y the whole square equals d2qp square plus d2pq square. Okay, this is actually an optimal. So it basically says that d2qp square plus d2pq square is in some sense an optimal transportation cost. It's the solution to a transportation cost problem. Okay, because the left hand side is a variational problem over all couplings of p and q. Now before proving this lemma, so let's say before showing this lemma, let's use it to so let's use it to show the base case. Of Marton's conditional transportation inequality. Okay, so let's define again the Radon-Nikodym derivative between q and p as r. So let r of x for every discrete outcome x be defined as the ratio q of x by p of x for all x. Then we can write this equality that says that d2 qp whole square plus d2 pq whole square is nothing but the expected value under the p measure of this quantity, 1 minus rx plus square plus rx minus 1 plus square divided by rx. This is easy to check, and let h of t denote the function 1 minus t log 1 minus t plus t for t less than 1, and h of 1 is defined to be 1. So this is the familiar h function that we have seen before while analyzing the tail of the Poisson distribution. It's connected intimately to moment generating functions of the Poisson random variable. One can prove this easy inequality that says that h of t is lower bounded by t square by 2 if t lies between 0 and 1, and t square by 2 1 minus t if t is negative. So this is something that you can easily check. Okay, and these bounds will come in very handy. By the way, h is also the same function that that was used to in the manipulations to derive the Bennett and Bernstein inequalities. So moving on, let us so with these lower bounds for h, we can actually use these lower bounds for h to bound each of these terms in the right hand side of the d2qp square plus d2pq square expression. So thus with this we can write that 1 minus r of x for any x, 1 minus rx plus square is just at most 2 times h of 1 minus rx plus. Okay, note that 1 minus rx plus is always bounded between 0 and 1, and on the other hand we have rx minus 1 plus square by rx is at most twice h of the negative of rx minus 1 plus, okay, which in turn yields that, so if you go back to d2qp square plus d2pq square and plugging in the upper bounds on the right hand side, we have d2qp square plus d2pq square is at most twice the expectation under p of h of 1 minus rx plus h of the negative of rx minus 1 plus, and this, if you write out explicitly, turns out to be exactly the sum over all x of px, the expectation under p of rx log rx plus 1 minus rx. Okay, so the second term just becomes 0 because it's the sum of px, which is 1, minus the sum of qx, which is again 1. So 1 minus 1 cancels out, and what remains is just twice the KL divergence between q and p. Okay, so what we have shown is that d2qp square plus d2pq square, assuming this lemma, so this lemma allows you to relate, it's a transportation cost lemma that allows you to basically say that there exists a coupling for which this equals d2qp square plus d2pq square, and what we have shown is the right hand side is upper bounded by twice dqp. So that completes the proof of Marton's conditional transportation cost inequality modulo the proof of the lemma. So let's now do the proof of the lemma to wrap up this entire discussion. So what does the lemma ask us to show? The lemma basically says find a coupling between x and y so that in some sense the conditional probabilities of discrepancy between x and y are kept to the least possible amount. Okay. So so let's take any coupling of x and y following the marginals p and q, given marginals p and q. We have that the probability of x equal to y given, so not discrepancy but equality. So probability that the joint pair lies on the diagonal given x equal to small x is by definition probability x equal to x, y equal to x divided by probability x equal to x. And you can, from the top numerator, you can factor out probability y equal to x into the conditional probability of x given y equal to x to show that this is bounded above. So because this is a conditional probability, it has to be bounded by 1 above, and it's also bounded by qx by px, which is what you get when you factor out the numerator as py into px given by. Okay, so therefore the expected value of p x not equal to y given x the whole square, which is one part of the lemma's left hand side, is lower bounded by the expected value 1 minus qx by px plus the whole square just by algebra, and this we know is equal to d2 square qp, okay, or d2 qp square. Okay, similarly if you condition on y, we have expected value that of p x not equal to y given y whole square is at least d2 pq whole square. Okay, so what we have shown is basically that the left hand side in the lemma is lower bounded by the right hand side. So this left hand side, the minimum value is at least the right hand side. Now what we have to complete in order to show to finish the proof is to show that there actually exists a coupling that attains equality. So we next exhibit a coupling attaining exactly d2 qp square plus d2 pq square. And what is this coupling? In fact, we can reuse the same coupling that we used to show the maximal coupling lemma. Okay, in fact, this is the same coupling we will used to show the maximum coupling lemma. Okay, recall what was the maximal coupling lemma we showed. Basically, we showed that there exists a coupling. So, rather the minimum over all couplings between P and Q of the probability of x not equal to y is equal to the total variation distance between P and Q. So we'll use the same coupling, and just to recall what that coupling was, so we drew a picture. Let me just recall that picture. So if you define A as the set where um, let's say A is the set of all x where P dominates Q. So we basically split this 2D square into A and A complement. This is A on the x part, A complement on the x part, A and A complement on the x and y parts. And this was the diagonal where we put as much probability mass as possible. And the remaining probability mass was all put on the northwest quadrant. here. Okay. So now let's just use the same coupling. So just to put it down formally, this coupling we called P star xy, which is just defined to be min px qx qy if x equal to y. It was defined to be px minus qx into qy minus py in the northwest quadrant divided by dtv, the total variation distance between p and q, on x belonging to a and y not belonging to a, and 0 otherwise. Okay, so that was exactly this coupling which put mass exactly on the diagonal and the remaining mass on the northwest corner. So we have in this case, so for this coupling, we can easily so we can evaluate p star x not equal to y given x equal to small x. Now what is probability x not equal to y given x equal to small x? Well, if x is equal to small x and small x is in A, then there is there is potentially some non-zero probability of y not equaling x. But on the other hand, if x is in A complement, then in fact y always has to be equal to x by our construction. Okay, so this can only be non-zero if small x lies in A. Okay, so this in fact is just by our construction, it is px minus qx plus divided by px. Okay, so the conditional probability for any, so if you look at the first vertical black line here, the probability that y is not equal to x given x is at this vertical x is at equal to small x is simply the probability of the segment in the northwest, the probability on the segment in the northwest corner divided by the total probability of this vertical line, which is px, and that's exactly what we've written. And this implies that the expected value of this probability, conditional probability squared, is just the sum over all x of, so imagine squaring the right hand side expression, so divided by a px square, but you also multiply by a px because you're taking expectation with respect to small x. We just get px in the denominator, sorry, as opposed to a px square. This is exactly d2 qp. Okay, and exactly along the same lines, we also have expected value of p star x not equal to y given y equal to small y whole square. Just by symmetry, in fact, you have this equal to d2pq. And that completes the proof of this lemma and hence of Marton's conditional transportation cost inequality. Thank you.